The binomial distribution is commonly thought of as only a discrete distribution. However, when our sample size becomes sufficiently large, we'll switch over to the normal approximation to the binomial example. The general rule of thumb is when our value of n times pi is greater than or equal to 10, then we switch over to the normal approximation to the binomial. So let's take a look at an example calculation. Let's suppose in a certain store there is a 0.03 probability that the scan price in the barcode scanner will not match the advertised price. Our cashier scans 100 items. That's our value of n. We can use that information in addition to the probability to calculate the expected number of mismatches, the standard deviation, and then the approximate normal probability of at least 20 mismatches and of more than 30 mismatches. So using this information, we're going to start with our value of n, which was 800, because that's how many items that the cashier scanned. Our value of pi, which was our probability, which is 0.03. And going back to our rule of thumb, if we were to calculate 800 times 0.03, that value would be greater than 10, which is why we're using the normal approximation to the binomial. So the first part of our calculation is the mean. Here we're calculating the mean by multiplying our value of n from cell B15 by pi, which is in cell B16. We can see the average number of mismatches is 24. So we would expect 24 out of 800 scans to be incorrect. So we can calculate our standard deviation, which is equal to the square root of n times pi, which is also equal to our mean. So we're using cell B20. That's multiplied by 1 minus pi, which was cell B16, and then we're taking the square root of that value. So our standard deviation is equal to 4.8249. So we have quite a bit of variation within our process as well. Using our mean and standard deviation then, we can solve for the probability of at least 20 mismatches. So here we're looking for an x value of 20. Since we're using the normal approximation, this is where it gets a little bit tricky and can be easy to forget, but we always want to take our x value, and since we're solving for it at least, we're taking x minus 0.5. So in this case, it will be 20 minus 0.5, or a value of 19.5. And we'll use that as our x value for the calculation. So our probability then, we'll calculate using our binomial distribution again, the binom.dist, and we're using our value from B29, which is our new x value of 19.5, our number of trials from B15, which was our 800, our probability, which is our pi value, which was 0.03, and we're looking for cumulative because it's at least, so it's more than, not exactly. And then because we're looking at everything to the right of the curve, we're using 1 minus to get that value. So that tells you that the probability of having at least 20 mismatches is 0.8237 or 82.37. Now this is important that we always go back and do a sanity check. Our average was 24, which means that 50% is higher than 24. Since we're looking for 20, we would expect our value to be greater than 0.5 because it's from the mean and more, so over. So our value of 0.8237 makes sense because it's going to be greater than our 50% when we get our value of 82%. When we look at 30 mismatches, however, that is going to fall to the right of our mean, so we would expect our probability to be less than 50%. To solve for 30 mismatches, now we're looking at more than. So before we were looking at less than, so we subtracted 0.5, so we included 20. Now we want more than 30, so it does not include 30, therefore we're going to add 0.5. So in this instance, it will be 30.5 that we're using for our value. Our probability is still going to be 1 minus the binomial distribution because we're looking at the right-hand side of the distribution. So we'll use a very similar calculation in that we're looking at our value of 30.5 for our x value in cell B35. B15 is our number of trials, which again was 800. B16 was our value of pi, and then it's still cumulative because it's everything over that. So here we get a value of 0.0925, or we have a probability of 9.25% that we have more than 30 mismatches. So again, we can use this information from a managerial's perspective to understand how many incorrect scans, because this is going to take longer for not only our employees then to scan items at checkout, but then also for our customers to get through the checkout line. So as we look at these numbers, these probabilities, we can use them to understand how it impacts our organization in terms of planning and scheduling. And we can also use it to drive continuous improvement and focus our efforts on improving the scanning process and reducing the number of scanning mismatches.